Hi, my name is Claudiu Barbura, and I work as an engineer for Atigeo. We're based in Seattle, Washington. And I work with an amazing group of engineers from Timișoara, Romania. They made all the demos that I'm going to be showing today possible. I'll go quickly through the introduction. So what's in the agenda? First, I'll present the xPatterns architecture. I'll explain what xPatterns is. Then I'll talk about how we evolved the stack from Hadoop to Badass, and then what are the contributions we added to the ecosystem. We'll touch on the lessons learned with Spark from 0.80 to until today. And then we'll do a lot of demos. So what is xPatterns? It's our flagship product. It's the big data analytics platform that really showcases all the experience we accumulated over the years in big data and in machine learning, NLP, and so forth. And what we have today is a platform that allows engineers, our engineer or external vendors, to build big data intelligent applications from a web console or through RESTful APIs. So we're abstracting a lot of the complexities that come with building these type of applications and providing enterprise-grade attributes to them, dealing with things like monitoring, operating them at scale, security, and so forth. So we cater to all these roles that you see on the right-hand side: ETL engineers, analysts, data scientists, application engineers. And what we have for them is tools and APIs that allow them to do things like ingesting data at scale, building an ELT pipeline, building a data warehouse, exploring the data warehouse after they transform the data, publishing data to NoSQL, SQL, or search, publishing models built on top of the data in the warehouse, scientific workflow, and experimentation component that allows to run multiple experiments and to deduplicate intermediate steps in those workflows. Again, publishing model data, all exposed through dashboards. So we have tools for everyone. I'm going to be showing, unfortunately, just a few of them. Time is short. So this is the reference architecture we built for our largest customers in healthcare. It doesn't have everything, all the services that we provided, but it's a good summary of all the services that we build around Spark, Shark, Mesos, Tachyon. So what we do, we ingest the data from multiple sources, SFT, S3, and we're integrating Talend for supporting all their data connectors in the number of 450 plus. Ingesting data into I call it the Mesos cluster, because we run Mesos as a resource manager where we combine multiple workloads, Spark and Shark, obviously, and we still have legacy Hadoop and Hive code and scripts. And more recently, we added Aurora. And data is the platform can be configured to not only do backups, but also do geo backups. So we're filling over to another cluster with the same characteristics on in a different region, for example. Or if we're deploying on-premise, we can handle geo-replication as well between multiple data centers. We're I guess, service provider agnostic. We can run in any cloud provider on-premise, running today on EC2. So once we have the ingestion sorted out in the backup and restore, then we have a transformation component that allows us to transform the data, to take it through various stages, to be prepared for building models or for being exposed to dashboards. So we have these arrows here that show how we export data into NoSQL. I'm going to be showing an example shortly here. Data in NoSQL is being geo-replicated in real time, or near real time, I should say, between two different data centers. We use Cassandra as our NoSQL store. And then we have, again, geo-replicated APIs, serving requests. We use Amazon's, because we're running at Amazon, we're using their service, their DNS service, that allows us to send users to the closest data center. We use something called latency-based resource record sets. So that's the architecture. And there is other services like Zookeeper for failover, for Mesos and Spark, for configuration management, Kafka for ingesting data through our APIs and so forth. So we evolved from Hadoop MapReduce to Spark, we use Core, Spark Core, and recently started POCing with GraphX. And most of the scripts in the ELT pipeline that we build we used to be in Hive. We converted them to Shark. Now working on adopting Spark 1.0 and Spark SQL. We use mostly the CLI and Shark Server 2 and something called JAWS, which we'll learn in a second. Then we moved from Node Resource Manager to Mesos. Mesos allows us to run multiple Spark job servers, multiple instances of JAWS, and Shark Server 2, Hadoop, and Aurora more recently. We also adopted Tachyon for things like sharing data between multiple Spark applications. We used to rely on the Hadoop distribution that we run on top of for dashboards. We now have Ganglia, and that solves the story. We don't have to show where a Cloud Data Manager or a monitoring dashboard from MapR or Hortonworks. Should mention we're Databricks certified. And I should call this BDAS++ because we added some contributions to the ecosystem. And what JAWS is our HTTP Spark SQL server, which we are outsourcing today. This has been done by the Alpha team in Romania, so thank you for that. We have the GitHub account. Hopefully you can download it, use it, give us feedback, contribute to it. We're working with the project committers to see maybe it can be adopted. Today we're running on 091 and Shark, and it used to be called, that's why we used to call this server the HTTP Shark server, but since we're adopting Spark SQL, we're going to support that as well. The API at the top will stay the same. So another contribution we want to make is the Spark job server. What we solve is this thorny issue of running multiple Spark contexts in the same JVM. It still doesn't work today. We had two approaches, one to fix it in the Spark core. We're very close to having a fix for that. But in the meantime, we wanted to have this running in our job server. So started off with Yola. We forked their code, but ended up doing so many invasive changes that it would be difficult to just push it back in the same folder. But we'll still contribute it back through our GitHub repository. Another thing we added is job submission in Java as well. Another contribution which really kept us up at night, long nights, is the framework starvation bug. Even though it's in Mesos, it had to do with running all our Spark context and Shark servers on top of Mesos. We fixed that. We submitted the patch. You'll see a detailed blog on the sign-up link displayed here. Another contribution we're working on are providing updates for the two scheduler backend implementation in Spark, the coarse grain and the Mesos one. So we can build these contexts, and so we can use an even distribution of resources among the clusters. And that's useful for our expert to know SQL tool. Our journey through Spark from 0.80 to 1.0, we started POCing in 0.80, lots of out-of-memory. Our first production deployment was done in 0.81. So we had this customer, we had 20 billion healthcare records, close to 200 terabytes of compressed HDFS data. Started off with Hadoop MapReduce, and then we built another cluster of 20 larger instances so we can leverage memory computation. Similar in cost. Obviously added some EBS volume there to make up for the loss in storage. And despite the fact that we had to really optimize every data set and every query, we still made huge progress. In the end, we cut down on the processing time, our daily processing time, from 14 hours to 1.5 hours. We also mixed Shark with Hive where it made sense, or whenever, at the time, Shark didn't support a few features that are now supported today. Then in 0.90, a lot of the problems were fixed, especially the one with the spilling on the reducer side. But we still required some patches that they provided. We're running on 0.91 today and upgrading to 1.0. I'm going to switch to demos now. Takes a while. Okay. So what do I do? I want to show demos. Let's see. Unplug. Any help from the folks in the back?
Do you mind reducing the resolution a bit?
Okay. No, we can do that, sure.
Might be an HD. Yeah, whatever.
Any questions in the meantime? So I don't waste the time. No questions.
I haven't seen this one before. I think.
Any questions in the meantime? There's a question. Can you take the microphone because I can barely hear you.
I think it might be a little communication error between the hardware and.
Hello? So the question was, like, what prompted you guys to move from, like, say, the Hadoop stack to the BDAS stack?
Okay, so that was a good question. What prompted us from moving from Hadoop to the new BDAS stack is really increasing performance and reducing operational cost. It was just costing us too much to run everything on Hadoop.
So you guys were in Hadoop 2 or like pre-Hadoop 2 without Yarn?
Now, we started before Yarn even came out. Yarn was in alpha. We started with Spark, and that's why we adopted Mesos. It was more mature at the time. And we still use it today, even though if we are asked to run on an existing Hadoop distribution, we would support Yarn. We POC'd in Yarn. The one thing I like about Mesos more than Yarn is that when running, we can run Spark in what we call now fine-grained mode, where resources are managed more efficiently, as opposed to the coarse-grained mode that you're supposed to run in Yarn, where you allocate a fixed number of CPU and memory, and you don't release that until you're done with the job. In fine-grained mode, with Mesos, resources are being allocated between different frameworks more efficiently. So there's no framework that really hogs a particular portion of the cluster, especially if you're running big jobs, like a Hadoop, for example. And we're running Hadoop on Mesos today.
All right, is this?
Yeah, it's fine. It's good. Thank you. So, yeah, good enough. Thanks. So we'll start with the ingestion tool. I'll demo building an application, a simple recommender system using collaborative filtering, a memory-based approach using vector similarity. So, like I said, we can connect to multiple data sources, S3 and SFTP being currently released, working towards integrating talent. So I'm going to select the data set, a job definition. I'm going to edit that. And now besides the S3 credentials, where my data set resides, we have something called parallelism level, which is really now triggering a Spark job behind the scene using unlimited, meaning running in fine-grained mode under Mesos, using the entire cluster, whatever it's being provided by Mesos, offered by Mesos, or using a fixed number of processor. For example, running against a SFTP server where you don't want to just invade that. you might want to throttle it through this control here. Once the jobs are running, we're exposing logs, status, and progress through web server sockets back to the UI. But there's also a full RESTful API that achieves the same goal, in case somebody wants to use it in a different fashion. So this tool behind the scene will download the file, will decompress, will encrypt, decrypt if needed for backing up in our S3 repositories, and we'll do also the geo backup, the geo failover if necessary, if it's configured that way. So let's assume we ran that. It's going to take a few tens of seconds now, which are precious. So I'm going to just show what is being ingested, this file that we need. Basically what the ingestion tool does, brings all the data into HDFS. That's our repository. Once you have the data in HDFS, now you ingested it, you want to do a transformation. You want to use a T component where you're allowed to build a data pipeline. You can do this in an interactive fashion. You can you can create a data pipeline consisting of multiple stages. Spark, Shark are out of the box now, and everything else Uzi supports. So you can build a complex execution graph, a complex DAG, and on top of what Uzi supports today, Hive and Shell and Java and so forth. And we also added Spark and Shark support. That's what we have on Spark 091. So it's somebody like an engineer that would build an application would have to write a Spark program. What they're required to do is let me show you some code, is to extend one of our interfaces, which will provide with a context and a logger. So everything they do in their Spark program is being logged, persisted. We're sending back to UI or the APIs. And the Spark context is necessary because we know whether it's using Mesos or not, whether it's failed over with Zookeeper or not. Engineers will just provide their code and we run it for them. Once we run their code, we're gonna display the exact details of running their job, all the stages that we have here. You see it? Yeah. So you have the three stages, the Spark stage that builds the recommender and shows exactly what it did. It connected to the Spark cluster. The Spark UI now is being exposed. So you can look at your execution graph, and providing back all the logs of executing that particular code. We have the similar story for Shark, where you can just provide a SQL script. In this case, once we build we computed the similarity between movies. Sorry, I should have said from the beginning. We downloaded a movie lens data set. It's a public data set that comes with the rating of movies from users. So in the Spark stage, we're building computing the similarity between movies. In the Shark stage, we're gonna do some slicing and dicing and compute predictions. We'll predict movies that, for example, a user liked and rated. We're gonna recommend movies that are similar to those that he rated highly. The code is here. Again, you're building your whatever script, HQL, we call it. But it can be any text-based file. And providing SQL scripts. They're running against Shark today. We're going to run against Spark SQL very soon. And what I'm doing at the end, I'm also loading it into Tachyon. So Tachyon is our in-memory distributed file system. We want to do this because we want to explore data faster. Once we're done with the pipeline, we want to explore it and run queries against it so we can analyze and observe. So let's assume we ran that. It's taking a few minutes. And it was successful. At the end, we build an email stage so we can send an email with a status. So the end result is we now have a few tables in the warehouse. So for that, we have a tool called the Warehouse Explorer. And that's using our open source HTTP server, and we build a nice UI on top of it. Let me try to squeeze this in here. So we have a metadata explorer that allows you to browse the database and all the tables with their schema. So we can quickly run queries against your table. We have a query editor that has autocomplete features. And we have a full history of all the queries that were run with all the logs, with all the results persisted. The HTTP server supports a pluggable persistent mechanism, either HDFS or Cassandra. So now we can look at the results from the tables we created in the pipeline. We can see execution, how long it took. You can look at the results, and once you observe your data, now you're ready to either build a model on top of this data, which I'm not showing today, or to publish to NoSQL. So we have a tool that does just that. Every time we would have to build, to expose data in the warehouse, whether it used to be Hive or now it's Shark, or SPASQL in the future, we never expose real-time services on top of that data. So what we do is we export it to Cassandra. That would take building a custom MapReduce Spark project that transfer data between the two systems, data access layers, APIs, all the ingredients of the APIs, resilience features, instrumentation, and so forth, geo-replication. So we decided to create a tool that does that interactively. So you can show how to create that. So you're creating a job name. I'll show it quickly. Then I have pre-created jobs, which I'll run. Once you create that, you connect it to a database. You can now drag your data source and create a mapping between the warehouse and Cassandra. Okay, I got it. Let me create a source quickly. It's exposing my tables. I'm dragging this. Tough time dragging it. Okay, I can drag. Fine. I won't drag anymore, so I'll just show a pre-created job. So in the mapping, you're specifying which fields you want to transfer over, what kind of transformation do you want to apply on those fields. You want to specify unique keys, so we know how to build an efficient data model in Cassandra. And it's not about transferring one-to-one records between the two systems. It's about building a model where both write operations and read operations are fast. At the end, what we do is the application engineer will actually provide the read access pattern. They know how to read the data, and they're defining the APIs. So once they define the API, they're specifying the lookup fields from the data set, from the mapping. At the end of running this job, they'll have a generated API that has all of the ingredients. It's geo-replicated, instrumented, and exposed data that was exported to Cassandra. And I think I'm getting close to finished. Any questions? I want to put something else.
Any questions? Yes, one.
That required, you said a logger, and what was the other parameter I think that was required?
Let's be the Spark context and the logger. If you wanted to use a logger to actually, in your Spark code, everything you log, we persist and we send back through APIs and in the UI, asynchronously. So we'd love your feedback, and here's a sign-up link to get in touch with us. We wanna expose this to early stage testers. Sign up and let us know if it works for you.
Okay, that was a cool demo, Claudio. Let's thank the speaker.
Thank you. Thank you very much.